So yeah, so I was saying that in terms of the best way to prepare, you might want to go ahead and just to start going over all the previous practices. Just recall that that is at the in here. Let me just see. Let me see. So, okay, so you check on the resources at the very end. We should have now all the test reviews. And so we have for test one, test two, test three, and final exam. And after this section, I'm going to be making available the solutions as well. So I'll say go over those solutions. Also, the worksheet solutions are a good way to actually check for difficult exercises because the worksheet were a little bit more complicated. So that is a way to also prepare. And last but not least, you have the practices. The extra practices, they do not have class value, but they're very similar in terms of what you saw in the homeworks. So that is a good source for extra practices. In terms of what you should prioritize, I'll say go with these practices first for all the tests that we've done. And you have the recordings and you have the solutions on them. Go over those first, and then after that, go over the practices. Does this sound like a plan? Okay. Do you have any specific questions that you would like me to go through? Any specific topics? For this final exam, I'm really going to go over a lot of the last things. So I'm not going to go over a lot of the previous stuff since I can consider that that is covered from the previous reviews. Okay. So do you have any particular topic you will want me to go through first? Otherwise, I'll just jump into the last part. Optimization. Okay. All right, that is a good topic. So in optimization, what happens is that you usually have two functions. You have like a function, or you have a couple of equations, actually. You have like equation 1, and you have equation 2. And equation 2 is usually a restriction of the variables. This is a restriction, or let's say a condition. And once that you plug these things together, then you're gonna get a function in terms of a single thing. And then there's where you optimize, getting the critical point and then plug it in. Then let me give you an example of that. So for example, in the last exam, we have this this question where we have a pen we're being built, and so we have a river on this side, and so we have this x here, and then we have y here, and the one in the exam we didn't have y here, but let's put y here. And so there's two ways that this is going to work. So we can talk about the area. So area is x times y, and then the perimeter, which is how much we use to cover this, which is 2x plus 2y. Then there are a couple things that you can do here, but for the most part, you can only have two options: make this the restriction or make this the restriction. So one, let's make a perimeter is equals to the condition. So let's say, for example, this is a pen and we're building this and we have 500 meters of, or 1,000 meters of wire to build this out. So this means that this 2,000 gotta be the 2x plus the 2y. And so this is why it's a condition. This is a restriction. This is telling me how much material I have. If I simplify this, I'm gonna have 500 is x plus y. And then I can put 500 minus x is equals y. And then I'm gonna replace that in the area function. And this is x times y is equals x times 500 minus x. And so now the area is a function just in terms of x. Okay. And so at that point, I can do now optimization. So, which is pretty much find the critical point, find what is the maximum. Here, the critical point is going to be given by this. So 500 minus 2x is the derivative. And so this means that 250 is the value that is going to make that 0. And so that is my critical point. I can find that is a maximum because I find the second derivative. And the second derivative is actually going to be minus 2. So a2 prime of 250 is minus 2, is less than 0. And x equals 250 is a maximum. So that's what the optimization does. Once that you find that, then you plug that in y. Y is 500 minus 250. And so you find that this is 250 as well. And that gives you the maximum dimensions of this. And so this is one of the cases where the condition was over the perimeter. And the one on your exam, you also have the condition being in A. That was what came in the exam 1. And so what that means is, like, for example, now I can say, well, I want the area to be, let's say, 500. The area is going to be 500. So this means that 500 is equals x times y. Now, so this changes the condition. And so now I can say, well, y is 500 over x. And so now instead of using maximization for the area, I can probably minimize perimeter. So the perimeter is 2x plus 2y. And then I can replace this as 2x plus twice 500 over x, or 2x plus 1,000 over x. Now, if you take the derivative, p prime is 2 minus 1,000 over x squared. And so from here, you can find out when this is going to be equals to 0. And that means that x squared is equals 500. And so x is equals to square root of 500. Okay. And so this is the square root of 5 times square root of 100, or 10 square root of 5. And so this will be the value that I pick here. Now, when I do p2 prime, this is just going to be 2,000 over x cubed. And this is always going to be positive. So x equals 10 squared of 5 is a minimum. And then from there, you do the same thing. You find the value of y. And then you obtain the dimensions that you're supposed to get. And so this is typically the same setup for everything that you do in terms of optimization. You might have different functions. Sometimes you have a function that is dependent on something else. So for example, you have like the canned example, or the kin exercise, where you have the surface area of this is 2 pi r times h plus, and then this is pi r squared by 2, so 2 pi r squared. So this is the kin. But then you have some sort of relationship that gives you how much is h. So I don't know, you can kind of say here, well, but the volume of the skin, which is pi r squared h, is only supposed to be 500, right? And so from here you get that 500, h is 500 over pi r squared, and then you get to replace everything in terms of r. And I think you can probably follow at this point that it's always going to be the same thing. Here, I just simplify these factors, and I'm going to have set up that depends of R, but it's essentially the same. Is that making sense? Yeah, so a lot of this is like find first what is the function that you want to maximize, and then find what is the function of the condition. You got to identify those two. And then put the maximizing function in terms of a single variable using the condition. And then from that, you can just take the derivative and just complete the exercise by finding the critical point and finding the maximums and minimums. Does that answer your question more or less? Do you have a particular exercise that you will want me to go through, or this is fine? Okay. Okay, so again, the final exam is comprehensive. And so that means it has everything from all the previous tests included. But here for this final exam, this last example is only going to include some new problems from the section 5.5, 6.1, and 6.5 to prepare you for the exams. Those were not heavily covered on the last time. Now, we can start with some multiple choice question, and here just is essentially I'm going over some integration parts, and this is mostly reflecting the substitution case. So for example, here we have t over 2t minus 1, and when we do substitution, we always want to take the integral that we have to an integral that is a basic antiderivative. So we want to have something like a power, 1 over u, an exponential, something like that. So we make the substitution here. We get u equals 2t minus 1, because that's the part that is complicated and everything. That denominator is too complex. So if we do that u, then immediately the du is just 2 dt. So we're going to be able to parse this very easily. And then that's going to transform the thing below and just u. Now we have a t on the top, but that t on the top we can transform in terms of the substitution. If we have that u is 2t minus 1, then we can just solve for t in terms of u. And it turns out that t is 1/2 of u plus 1. Now, if we replace that here, then notice that the next thing that we have to replace is what are the limits of integration. So we got to replace 1 by u of 1 and 2 by u of 2. And in this case, because u is 2t minus 1, then when t is equals 1, u is going to be 1. And when t is equals 2, then u is going to be equals 3. Now, this simplifies a little bit more the situation, because then I can factor out a lot of this constant. So this is 1 over 4. And then I can divide u by u and 1 by u. And so that's going to make a very much simpler integral here. This is going to give me 1/4 of u plus 1/4 of log of u. And then I can plug this and the values 1 and 3. And so that's as one example of substitution here. Again, with the substitution method, what we always trying to do is simplify so we can have just one single variable being used, or one easy antiderivative as well being used. So for example, in this case, this is one of the ones that I think I did in the worksheet or in the practice, because the sine square is the complicated term, but we can think of u being equals the sine. Then this is going to give me a power, u squared here. And if u is equal to sine, then the u is going to be the cosine. So that's going to take away this term. And this is just going to be u to the 3 divided by 3. And between 0 and pi half, that's just going to give me plug in the values that we have. Is going to give me sine of pi half, in, which is 1. And so that will give me 1/3. It all in just the value here. Okay. Now, sometimes you're going to have integrals that are sum or subtraction of things that are looking very similar to antiderivatives that you might have. So for example, here, number 3, we have the integral from 0 to 1 of 2 over 1 plus t squared. And notice that this is an arctangent. I can put in front that too. And so that's just going to be arctangent, the derivative of arctangent. So when we integrate 1 over 1 plus t squared, that's going to give me 2 arctangent of t. On the other hand, this if I had this t on the top, although this looks very familiar and I could potentially go with a trigonometric substitution, the easiest way is just go with substitution. U equals 1 plus t squared. The u is going to be 2t, and so I'm going to have 1t on the top. That's going to help me out work with that. And I can simply get just log of 1 plus t squared. And so that's precisely what we get here. Notice we get the arctangent from the first integral. And then for the second one, we just made that substitution. And that's just going to give me 1/2 of log of u. And it's going to be between the new limits that I get that are between 1 and 2. Is making sense so far, everything? Okay. Okay, so now one of the formulas that is something that you can check is what is the average value over a certain function. And so let me just write that. But the average value of a function is 1 over b minus a of the integral of a to v of f of x dx. And so if you're talking about the average value of this function, and it's over the interval 1 to 3, then this is just 1 over 3 minus 1, integral of 1 to 3 of 4 plus 2x over x squared dx. And then notice that when this is set up, then that's just like a regular integration. You can split 4 over x squared and x over x squared. And then you can just simplify that. That's going to give me 4 over x squared over 4x to the minus 2. And 2 over x, x over x squared is going to give you just x to the minus 1. And so from there, it's much more easier to just integrate and then plug in the numbers. And you got to be careful that you're always plugging first on the superior limit and then minus on the inferior limit. You got to be careful if you obtain any negative numbers when you're integrating, because those negative numbers are going to be transformed when you plug on the second integration limit with the -1 value. Okay. So hopefully that makes sense. Now, another thing that is part of this last sessions is the notion of area. And the area of a function can be given by multiple things. Sometimes it's the area between two different curves, or sometimes it's just between a specific boundary. In this exercise here, we have that we have y equals x squared, but we're not checking the area under the curve. We're actually checking the area between a certain number of points. So between the curve, between 0, 0, between 2, 0, which is 2, 0 here. Is the area between the rectangle with 4 vertices and the curve y equals x squared. Okay, and so we have 2, 4, which is this one here, and 0, 4. But the shaded region is the top. So this shaded region is going to be given as an area, is the area from 0 to 2 in terms of the integral. And now we got to check the difference of two y values. Notice that this is y equals 4 on the top. That is that line. This line over here is 4. And then minus, and then the curve that is bounded below is x squared. So this is the area. You gotta be very careful because this is not the area under x squared. This is the area enclosed by this lines and the curve. Okay. So the graphical means are very important here. So this is going to give me 4x minus x cubed over 3, and then plug between 0 and 2. Clearly in 0, this is 0. So only is going to matter in 2. So this is 8 minus a over 3. And so this is going to be 16 over 3. Making sense so far? Questions? Okay, you can see here the solutions as well. So now let's do another one with this area. Notice this, find the area of the region enclosed by these two curves. This one is going to be a little bit more involved since it has two different functions. But every time that you are doing an area, you got to question yourself in two different things before you start. And the first one is, who is the function that is on top? Because the area between two curves is going to be defined as the integral of the curve on top minus the curve on the bottom. Okay. And this is the limit of the integration. This point here are going to be the crossing points. So this and this are crossing points. Of the two curves. So in this case, for example, it's very easy to identify the curve on top in this area at least is 4 minus x squared, which is the parabola here on top. And the line y equals 1 minus 2x is in the bottom. So at least I can start with that. I have the top and the bottom very clear. 4 minus x squared is the curve on the top. Minus, and then 1 minus 2x is the bottom. And now you gotta look for where those points are going to cross. So you can see here that they're crossing in -1 and 3. And that is because you can see it graphically here. But you can also wonder, how do I get those values? How do I find those crossings? And you can do that by making the two functions equal. So 4 minus x squared is equals 1 minus 2x. And so just solve this equation. To solve this equation, we put everything in one single side. We have x squared minus 2x, and then this 4 moves to the other side, plus 5. So here, you factor, and you want to know numbers that can give you this. And so you can go initially for trying to factor by two numbers such that the multiplication gives you 5, which is just not a lot. It's just 5 and 1, since 5 is actually a prime number. So this is not going to look like it's going to work out, because this should give me 5 and 1. But 5 and 1 under no combinations are going to give me this minus 2. So I'm going to have to just use a quadratic equation here. Wait a minute. No, I made a mistake here. This 4 crosses to the other side as a minus 4. So this is a minus 4. And plus 1, then it becomes a minus 3. So now it kind of maybe makes sense. Multiplication should give you a minus 3, and the sum should give you a minus 2. Yeah, x minus 3, x plus 1. So you got to be careful here when you move the sign, so otherwise you might get a mistake that is going to completely change your integration limit, like I was just having that issue. Now, from here, notice I get x minus 3 got to be equals to 0, or x plus 1 equals to 0. And then from there you find, oh, x is equals 3, or x is equals minus 1, which are the limits of integration here. And this is one of the most important parts of doing areas, which is the setup in here of this type of question. Then after that is just the calculation, of course. You can take a look at here. You gotta be careful with the distribution of the signs, but once that you get that done, and you make sure that your area is positive, because that's the other thing. If your area is giving you a negative number, then something is wrong. But if your area is positive, then that's what's going to tell you that you're in the right track, at least in terms of who is supposed to be on top, bottom, or in the possible intersection points. Now, sometimes what you're gonna find is that the area is not as easy to find out in terms of a certain setups. So for example, we have a sketch the region enclosed by the curve by x equals y minus 1 minus y plus 1, and x equals 3 minus y squared. So this is a curve that is in terms of y. And notice that if we integrate with respect to x or y, is going to determine how hard things are. So if we integrate in terms of y, which is probably the easiest, we got to flip our head a little bit and see that this is the function in top and that the line is the function on the bottom. So if we solve to find the intersection points, we make those two things equals. And we did exactly the same thing that we did in the previous example. We're going to find that y minus 1 and y equals 2 are the points of crossing. And so we can set up the areas, the integral from minus 1 to 2, 3 minus y squared minus y plus 1, which is top function minus bottom function. And that's going to give me, after integration, 9.5. And so that's the area, okay? Now, this is if I decide to integrate this in terms of y, but if I decide to integrate that in terms of x, it will be a much more complicated situation. So actually, let me go ahead and just showcase that to you, just for the sake of the example. Notice that if I want to do in terms of y, then I gotta flip it around. And in terms of x, I gotta flip it around. And then if x is equals 3 minus y squared, then y squared is 3 minus x. And then y is gonna be square root of 3 minus x. And this is the positive. Yeah, this is the positive on the top. So if I'm talking about this curve is the positive, but down here will be negative. So it kind of depends on where is it. You can see this piece here below the x-axis is given by minus square root of 3 minus x. So why is that relevant? Well, you'll see in a second. Now for the function x equals 1 minus y, then simply y is transforming y minus x. So not a big deal in there. And then the area can be seen as and this is between minus 1 and 2 before. So y was minus 1 and y was 2. So if I'm changing this, when y is equals minus 1, then this becomes x equals 2. And when y is equals 2, this becomes minus 1. And so those are, so wait a minute. So this is minus 1, this crossing here, and this other crossing here is going to be 2. And so this will be the integral from minus 1 to 2. This is this piece from minus 1 to 2. And so the top will be a square root of 3 minus x minus, and then the line that is going to be 1 minus x. But this is just one piece. This is up to this point. And so plus, I also got to go from 2 to 3 of the top, which is a square root of 3 minus x, minus the bottom, which is minus the square root of 3 minus x. So overall, if we're going to go with this in terms of x, this is going to give me two integrals. First integral is this, and then plus another piece of the area, which is twice square root of 3 minus x. So, so as you can see, depending on if you do it by y or x, you can have a much more complicated, a much more easier approach to the same exercise. Does that make sense? Anish? All right, so that's pretty much a summary of all the things that in terms of the last couple of sessions, which is substitution, area, and average. Let me see what else can I fundamental calculus theorem can be something that I could include in here. So these are more in average values. Let me look at fundamental calculus theorem exercise, just to cover all the subjects. This is more of integration by substitution. Yeah, so I'm not gonna dwell on integration by substitution since that's something that you can check on the solution. But important topic is, of course, the fundamental calculus theorem. And that has two versions. And version number one is like if you have the function, the integral, if f of x is the integral from a to x of some function g of t dt, then you're gonna have that f prime is just pretty much g prime of x. So essentially we're saying the derivative of the integral that's what we're saying. The derivative of integral is just, sorry, this is g of x, not g prime. The derivative of the integral is just a function inside. This is another way of interpreting this. Sometimes you're going to have that you have a much more complex functioning here. So for example, if I have a equals h of x and I have g of t here dt, then f prime is just going to be a composition. It's just going to be g composed in h of x by the derivative of this, which is h prime. And so that might be one of the exercise that you'll see. Something like f of x is equals to the integral from x squared to sine of x of 1 over x t cubed plus 1. And so notice that this is a very weird integral that you probably won't be able to find very easily the solution. But the point is that you're not trying to find a solution. You're most of the times with this weird integrals, you're trying to find what is f prime. And f prime is just simply the function that is inside, but just plug in whatever the limit of integration is. And multiply by the chain rule, which so by the derivative of what the limit of integration is, minus, and then plug in the other function. And then multiply by the chain rule here. Is that making sense? So this type of exercise is really common. What else? The second part of the fundamental calculus theorem is that essentially if you already have the, let's say, f of x is the integral of a to x of g of t dt, then if you have just g of, or really without limits, just like this, then if you want to find out, let's say, the integral of a to v of g of x, then that's just going to be plugged into the streams, f of b minus f of a. And the way that you're actually using this is by, for example, when you do substitution, sometimes you're like, well, we can wait until later to actually plug the value. So for example, if I do 1 to 2 of log of x over x. And so this is something that I can kind of forget about the limit of integration for a bit and say log of x dx is just going to be, let me find out, u equals log of x, du is 1 over x dx. So I can see this as substitution. I can see this as u du with the substitution. And so this is going to be u squared over 2 plus c, or just simply log of x squared over 2 plus c. And so this is the antiderivative. This is the function f of x. So if I know this is the antiderivative, then I can say, well, then if I'm doing this one, then the integral of 1 to 2 of L of x over x is just equals to f of 2 minus f of 1. which is essentially is I just found this antiderivative first, and I'm just gonna plug on it. I'm just gonna plug on it in 1 and 2. It's exactly the same thing. So this is like log of 2 over 2. Square plus c, and then minus, and then plug on 1, which is 0 plus c. And so the c's are going to go away. And this is just going to give me the log of 2 squared over 2. Does that make sense? Okay, do you have any questions at this point? Anything that's coming up at this instance of the review? Okay, let me see if I can pull like a different exercise from the first couple parts. It seems like I have a picture here that I can use. Okay, so let's do some examples here with piecewise functions. Piecewise function is something that we use often to just double check what happens with continuity, with limits. So for example, we can talk about here, what is the limit when, let's say h, because here the variable is h, is going to -2 of the function b of h, because that's the function that we have over here. Now, the problem here is that the right side and the left side are going to different places. The left side is going down here, and the right side is going over here. So if I think about the left side is going towards, like, say, 1. But the limit when h goes to -2 by the right side, that is going to like 5. So this limit overall, when h goes to 2, does not exist, right? This is the definition of limit. And so that also means that b prime of 2 does not exist, because the function is not continuous, and if it's not continuous, it's not differentiable. The derivative does not exist. Okay. Same thing happens in limit when h goes to 3, bh. We also have a do not exist situation. Here is a little bit different, the reasons of why. Well, it really isn't, is the side limits do not match up. The limit when h goes to 3 by the right side of b is going to -1, but the limit when h goes to 3 by the left side of bh is actually going down. Well, this seems like it has a finite. I was thinking that maybe it goes to -infinity, but this is stops in here at -7. So it's kind of the same reason. And another thing that you might want to check is what are the values of the function. So for example, f of b of 2, or -2, sorry. B of -2 is actually -1 because it's where the value is being filled. Here we have a open ball, so it's not the value in there. And it's the same thing for 3. B of 3 is actually -7 because that's where the ball is being filled. Okay. Values like, for example, B of H is a do not exist because we don't have anything represented in there in none of the sides. And notice that for points like 3 and 2, then we also have that the derivative is not going to exist because there's no continuity. However, there are points where we can find the derivative here. So for example, B of 0 or B prime of 0 is a point where the derivative is flat. So this, we're going to find out that this is 0. We can find the value here. We can actually find out some other values. So for example, we can probably find the derivative and 5, and we can probably find the derivative of 6. Because simply those are going to be the values of this slopes, of the slope of this line. Because they're lines, the derivatives are going to be just the slope of these lines. So -5 and then 6. What is it specifically? I don't know, but I can probably find out. So for example, if I picked 2 points that seems to be over this line, maybe I can take in 3, this is like -1. So in 3 it's -1, and in 8 and in 8 was supposed to be 6. Notice that these are not the values itself, but it's what they're supposed to go over that line. So this is 6 minus 3 is 3, and this is 8 plus 1 is 9. So this is like 1/3. So 1/3 is the slope of this line. So that's going to be the derivative in 6. And a similar step I can take over this, just pick 2 points over this line to find the slope. And that's going to help me out finding the derivative at that given point. Does that make sense, Anish? Am I pronouncing your name right? Okay. Okay. What else? In terms of derivatives, it's always good that you practice the rules. And so just to finish up this session, I can say, well, just always remember, let's say you have 2 functions, h, let's say x squared, and like g equals, I don't know, sine of x. And so when you're doing different things, the rules with derivatives are going to work out different. So for example, if let's say f is h over g, then just recall what the derivative of those functions are. Don't be formulaic, just remember what it does. So for example, this will be h prime times g minus h times g prime over g squared. And so that will be for the ratio of this. So this would be like 2x sine of x minus x squared cosine over sine squared. And depending on what it does, so for example, here with the product rule, f prime is h prime times g plus h times g prime. So same thing, but with a plus in here. But you can also have compositions. So for example, f h composed in g of x. And so that implies that f prime is going to go with chain rule. H prime compose g of x times g prime of x. And so in chain rule, it helps that you identify who is each of the functions. So for example, because g is sine of x and g prime is cosine, so you can probably do cosine here right away. and h prime is 2x, so this is going to be 2, but instead of x, it's going to be gx, so 2 sine of x cosine of x. And notice that h of g of x is just sine of x composing here, so this would be like sine square. And so it kind of makes sense that this is 2 sine of x times cosine of x. Is that making sense so far? Another good thing is implicit differentiation, which is another way of having to differentiate. So for example, a very common exercise that you come across is find the slope of tangent line at certain point x0, y0 equals for the function or for let's say x squared minus 2xy plus y squared equals 1. And so we can say here that this is let's see. Yeah, at the point let me just fix this here. Four. Let's put a 4 here. And let's put 1 minus 1 here. So I want to verify that this point goes through this. So this is like 1 squared minus 2, 1 minus 1 plus 1 squared. And so this is 1, and this here produces a 2 plus 2, and then plus 1. So this equals 4. So now I know that it passes through this point, so I know that it's going to be able to be a tangent line at this point. So this is the first thing that I wanted to verify. Now, the next part is, well, I want to find the slope, but the slope is the y dx, right? And the equation of the line is y minus the point, x0 minus equals mx minus x0. And so to do that, then we take the derivative here. But there's a chain rule here because y is equals to y of x. So this means that every time that we take derivative of y, we're going to multiply by y prime. So if we take derivative of this, is 2x minus twice, and this is a product rule. So here we have derivative of x is 1 times y plus x times 1 from the derivative of y times y prime, because we just take derivative of y. And then plus 2y times y prime equals 0. So now we got to find out who is the y prime. So we're going to leave everything with y prime on one side and everything without y prime on the other side. So we get 2x minus 2y from this piece minus 2x y prime plus 2y y prime equals 0. So now we're going to move terms without y prime to this side, and we're going to factor here y prime factor of minus 2x plus 2y equals to 2y minus 2x. I move these terms to the other side, so they change signs. So now y prime is going to be 2y minus 2x. And here we're going to have minus 2x plus 2y. And so this is the derivative. This is the y dx. But because we need the slope, then we do the y dx in the point x equals 1, y equals minus 1, which is the point that we started with. And so we plug, and so this is 2 times minus 1. Minus 2 times 1 over minus 2 times 1 plus 2 times minus 1. So this here is minus 2 minus 4. And this here is minus 2 minus 4. So it's going to be slope 1. And so now we can replace the values to actually get the slope, the equation of the line. So the equation of the line will be y minus minus 1 equals 1 x minus 1. So y plus 1 equals x minus 1, or that implies that y is equals x minus 2. And that is the equation of the line that is tangent at this point to this curve. So that's one of the classical exercises of implicit differentiation. Okay, so this is just a small sample of the things that I can go through for this final exam practice. But you should definitely go over all the topics that are possible, and just make sure that you visit all the previous topics, not only chain rule, but continuity, and it has a very different presentation. I'm missing to go over a lot of the stuff here, basic integration, related rates, all that kind of things. So it's worth going back to the previous topics, to the previous exams, and just practice with the previous text practices. Right, I think this is a good point to stop. Do you have any other questions, Anish? Nope. Okay. Well, thank you for attending to the session, to the preparation session. And yeah, like I was saying, just go over the previous stuff. That's one of the good ways that you have for preparing.